Ready?
Start.
Hi, today I'll be taking you through my research project, which is the comparison of prototyping methods for HTS generators. Firstly, we have two types of wind turbines, the fixed speed turbines and the variable speed turbines. Due to a number of reasons such as high energy yield, most of the generators being used today are variable speed turbines. Now, there are three popular variable speed turbines. Those are the double fed induction generator, commonly known as DFIGs, the direct driven synchronous generator, and the permanent magnet generator. If we are speaking about the double fed induction generator, it is the most popular with over 50% of the market share in today's wind farms, and the DFIG requires a gearbox for operation. This is due to the fact that the rotor speeds, the rotor spins slowly, but the generator needs a higher rate of rotation. Therefore, you need a gearbox to convert the slow rotation into the higher rotation speeds needed by the DFIG. They also employ a power control converter, which is about 25% of their rated power, and this gives them a range of around 60 to 100%. That's the operational range. That means they can operate at around 60 to 10% of the rated wind speeds. This range allows them to have an optimal tip speed for most wind speeds, and that means high energy yields are possible. But this is a geared system. The DFIG is a geared system, and the problem with geared systems are that even though they have failure frequencies that might be lower or are about average, as you can see from this graph, they have the highest number of hours per failure. You can see one failure of the gearbox leads to around 330 hours of downtime. And this becomes a problem because gearboxes, when you aggregate the failure frequency and the hours lost per one, it becomes the subsystem with the highest that contributes to the downtime the most. And because of this, we need to look at technology that does not use the gearbox, and therefore we come to direct-driven systems. Direct-driven systems such as the direct-driven synchronous generator have generators that rotate at exactly the same speed as the rotor outside. The problem with this is that they need full-scale power converters, which makes them a little more expensive, and they require low-speed, high-torque generators, as I mentioned before. These low-speed, high-torque generators are more expensive, heavier, and larger. So if we take a look at this table, we can see that direct-driven synchronous generators and direct-driven PM permanent magnet synchronous generators are compared with the DFIGs. If we say the DFIG is a standard model and make everything 100%, we can see that the direct-driven synchronous generator is 850% heavier and also 600% larger in diameter, while all the others remain almost the same, except for the permanent magnet generator, where the power losses are at 65%. And this is because the permanent magnet generators are not electrically excited machines. They have permanent magnets in their rotor, so the electrical excitation of the rotor can be eliminated, which means that they have higher energy yields. And also the lack of components such as slip rings found in most electrically excited machines are not found in PMGs, which makes them more reliable. But at capacities such as 10 megawatt, the rotor speed is so low that the size of the PMGs needed becomes so big that it's impractical. Now to solve the problem with these bigger speeds, at these lower speeds, we come to superconducting generators. Now the superconducting generators works by having superconducting wires inside the rotor to produce a magnetic field, and because the DC resistance is eliminated in these windings, the field current is increased. That means the magnetic field in the air gap is 2 to 3 times higher than what you'd find in a synchronous generator or permanent magnet generator, which in turn means that the generators themselves are 2 to 3 times smaller for the same power. And because they are smaller, you can easily deploy them out at sea, where the bases and the transportation and maintenance becomes cheap overall. Now superconducting wires are of two types. There's the low temperature superconductor and the high temperature superconductor. As you can see, the low temperature superconductor operates at 4K, which is very low, so the only technology being looked at seriously is the HTS, which has 30 to 50K operational speed. They are being looked at seriously because the cryogenic technologies to keep the temperature are already available in the marketplace and can be bought off the shelf. So there are a lot of HTS generators that have been proposed, and these generators need to be tested. So there are 3 types of testing methods. One is computer simulations using finite element method analysis, and then you get smaller scale versions of larger scale generators, that's small scale prototyping, and partial construction of a section of a full generator. So if you are going to talk about small scale prototyping, it's where you make a smaller version of the actual generator that is being proposed. It allows the feasibility and operational performance of a system to be gauged at a low cost, and it allows the identification of design challenges. Now if you are talking about partial construction, it's usually a pole pair arrangement of the rotor with a section of the stator, and you can see that the swing arms are there, the load cell, and all of this. So this is only this part is the section of the rotor stator section of the full scale generator, and this method allows the engineering challenges of the subsystems, such as the cryogenic systems, the fault ride-through capability, to be assessed reliably and effectively. So the engineering challenges of the full-scale model could be easily identified through this model. Now the research question. As you can see, each of the test methods have their own advantages and disadvantages, and allows us to understand the different design challenges or engineering challenges in detail. But they are not the same. So what we propose in this study is to identify the advantages and disadvantages and the costs associated with each type of testing method, and then we will see the limitations of each type of study. Now the design. The design is causal comparative, because we don't need a control group, we are just analyzing the different methods. And if we did have a control group, it will be the computer simulations, because they will allow us to compare all the other two together. The strengths we could and thank you. Arun.
की मिला?
The